So in the workshop, we'll look more into waves, mostly qualitatively. So there's a PhET simulation that you can find from this website here, where you can simulate a wave and we'll pick out the amplitude and the wavelength of the wave and determine the speed for a given frequency. So the first part of the workshop sorts of just visualizing the wave and different parts of the wave, if you'd like to call wavelength, amplitude as parts of the wave, and looking what affects the speed of the wave. For example, does amplitude and wavelength affect the speed of the wave, like so. We'll also see how the frequency of oscillation will affect the speed of the wave. Okay. And in the last part, the second part of the workshop, this is where we will look more into standing waves, as I've mentioned earlier, relating the frequency of the standing wave. We'll talk about first harmonics, second harmonics, and so on, and how is the frequency of the wave related to the wavelength of a standing wave. Yeah. So I'll give you time to look over this workshop as well. So again, 11:30, we can start looking at the answers to the workshop. Good. Right. Okay, everyone. So let's look at some answers and solutions to some of the questions in the worksheet. So we're not going to go over the simulation step by step, but you can do that, and it's also nice for you to do it so you can learn by doing. But we'll just answer some general questions and look at patterns here. So yeah, so in the first one, if you can see here, if you make the thing oscillate, notice how it's oscillating up and down, but the wave is propagating to the right. Yeah, so you have their perpendicular, so it's traveling perpendicular. So the wave is traveling perpendicular to the disturbance, and therefore it's a transverse wave. And if you explore here in this table, in step number 3, you're exploring the effect of the wavelength to the speed of the wave. You're exploring the effect of the amplitude to the wavelength of the wave. Yeah, so the first one was done for you, so you can try to set the settings to 0.75 centimeter amplitude, 0.55, and the wavelength, you can measure that by using the ruler. So you can drag the ruler and measure between 2 successive points. This is probably because I don't have one whole wave. So just use the ruler to measure between 2 successive points, and that should give you the wavelength. And from there, you can calculate the speed, wavelength times the frequency. So make sure your wavelengths are in meters, so that your speed will be in meters per second. Hertz is of course 1 divided by second. So multiplying 0.55 with 0.022 will get 0.012. If you do the whole exercise, you will see that, yeah, actually, who did the exercise? Did you see any change in the wavelength and speed, and therefore the speed? When you change the amplitude, did you observe any change in the wavelength? So the amplitude can of course be changed by changing this, and it will change how vigorously the oscillation will. So actually, why don't we do that? So that's a small amplitude. Measure the wavelength. And this is just half a wavelength. And then increase the amplitude. You will find that you'll actually get the same wavelength. You'll find that the wavelength will not change. And because the wavelength did not change and speed is related to the wavelength, you'll find that the speed should also be the same. So again, I leave it to you to do the simulation yourself and check that the wavelength indeed did not change. But that means that if the amplitude increases, so even if you have their amplitude increasing, you should still see that the wavelength stays the same. And since the wavelength stays the same, the speed of the wave should still be the same. Speed is only related to the wavelengths and not the amplitude of the wave. So for this second part, you're exploring how the frequency will affect the wavelength and the speed of the wave. So we're keeping the amplitude the same, 0.75 centimeters. The frequency we are increasing. So you can change the frequency in the simulation. The first one was done for you, and so you can check whether the settings are for your amplitude and frequency. If you have these amplitudes and frequency set correctly, then you should get this. So the measurement of the wavelength, because you're using the ruler, will have a little bit of uncertainty, but it should be close to 4.2 centimeters. If you increase the frequency to 0.7 hertz, you'll see an increase in the wavelength about 1.8 centimeters, further increasing the frequency to 1.4 hertz. Decrease. So you'll see that the wavelength will be decreasing. And I'll just put the answers here so you can check your simulations while you're doing them. But you can see here that the wavelength should change if the frequency of oscillation changes. And again, for the speed, you calculate that by multiplying the wavelength with the frequency. The frequency changes and the wavelength. So the frequency increases. Notice how the wavelength decreases and speed. So it means the frequency increases and the wavelength decreases. So an increase in one sort of cancels out the decrease in the other. So you'll find that if you do calculate the speed, you should get almost same speed. So from this, you can see the pattern that when the frequency increases, the wavelength decreases. Okay, and if if one increases when the other decreases, then that's the inverse relationship, right? So we've been using inverse and direct relationship already before. You can also see this from the equation. So from the equation, speed is equal to wavelength times the frequency. if you're comparing two variables, so here you're comparing the frequency with the wavelength, you need to rearrange your equation so that so that they're on opposite sides of the equal sign. So if you rearrange this equation to isolate wavelength, so we divide both sides with frequency, and that cancels out frequency, then you can see that the wavelength is equal to speed divided by the frequency. And so you can see here that the frequency is inversely proportional to the wavelength. Yeah? If the frequency increases, the wavelength decreases. Right. So the next one, you're keeping everything. So amplitude and frequency are kept constant, and now we're looking at the effect of tension. So this is something new. We haven't seen the concept of tension in the lecture. It's because in the lecture we were discussing more about waves in general, but for tension, this is specific to a wave on the string. Okay, such as the simulation here. So you have here a string, and you can change the tension from this. You can have low tension, middle or medium tension, and high tension. And this part of the workshop lets us investigate the effect of the tension. So if you're pulling the string more, what's the effect of that on the wave, the speed of the wave, as opposed to when you're loosely holding the string. So just some example figures here. For the first one, you should get a wavelength of about 0.5 centimeters or 0.05 meters. If you do, again, speed is equal to wavelength times frequency, so multiplying 0.005 times 2.4, that should give you a speed of 0.012 meters per second. For the medium tension, you'll have a wavelength of about 1.6 centimeters, 0.016 meters, and a speed of 0.038. And high tension, 2.6 centimeters, 0.026 meters, gives you a speed of 0.062 meters per second. So here, looking at how the wavelength changes, notice that the wavelength increases as you go this way. And as the wavelength increases, notice how the speed also increases. So when the wavelength increases, the speed should also increase. And if one increases when the other increases, that's a direct relationship. And you can also see that from the equation, speed is equal to wavelength times the frequency. So they are directly proportional in the equation. Okay, so I think up to this point, it should be fairly straightforward looking at the simulations. Now for this next part, it's a little bit more tricky because it requires some rearranging. So the equation for the speed of the wave on a string is this. So of course, it will also hold that speed is equal to wavelength times frequency. This is a general equation for all waves. But specifically for a wave on a string, we can relate the speed of the wave along that string to the physical parameters of the string, such as the mass of the string and the tension of the string via this equation. So this equation is just specific two waves on a string. And we're given that the maximum tension, okay, from here, this high tension, that's the maximum tension, is 10 newtons. We want to find the linear mass density, M over L of the string. So of course, from the previous question, so you have tension is equal to 10 newtons. And then from the previous exercise, high tension, that's the maximum tension. And for the maximum tension, the speed was calculated to be 0.062 meters per second. So speed 0.62 meters per second. And you're being asked to find what is M divided by L. Okay, so we need to rearrange the equation. To isolate M over L. Okay. Right, it's a little bit tricky because M over L is in the denominator. The easiest is when you're rearranging division and what you want to isolate is in the numerator. That's easier. But so what we can do to make this easier is to flip the equation. Okay, we flip both sides of the equation, we're not changing anything. So you can do anything to an equation as long as you do that thing to both sides of the equal sign. You're not changing the equation, it will still be a valid equation. So all we did here was to flip the equation, that we have to flip both sides of the equal sign so that V becomes 1 divided by V. And the right side becomes M over L divided by T. And that makes it easier to rearrange, to isolate M over L. And I'll do the rearranging using, the building up the equation. So you start with M over L, what you want to isolate. You divide that by T. So you have M over L divided by T, and then you get the square roots, and you have M over L divided by T, and that has built the equation for 1 over V. Then you go the opposite way. So starting from 1 over V, inverse operation of a square root is exponent 2 or square. That means you have to square 1 over V. I have to change exponent 2 or square. That means you have 1 over V and you have to square the whole thing. That's also equal to 1 over V squared, because 1 squared is still 1 and V squared. Right, and then do the reverse of the division, which is a multiplication. So you have to multiply with T, so you have 1 over V squared times T. And that gives you M over L. Therefore, M over L is equal to 1 over V squared times T, or that is simply T over V squared. Yeah. Right. So it's now just a matter of plugging in the numbers. 10 Newton for the tension and speed 0.062. Don't forget to square that. M over L will be 2601 kilograms per meter. Kilograms because it's mass divided by length. The unit for mass is kilograms. The unit for length is meters. So as long as you've got your tension in newtons, the unit here, newtons divided by meters squared per second squared, but newtons is of course kilograms per meter second squared. The units will all work out to be kilograms over meters. Okay. All right, so I guess rearranging this equation was the trickiest bit here. Once you've rearranged that, it's a matter of plugging in the numbers. Okay, the last one is for the standing waves. Okay, this one you really have to use the simulation to visualize this. So the amplitude 0.1, tension high. You can use any amplitude because as we've seen earlier, the amplitude does not really affect the wavelength and the speed. So if amplitude of 0.1 is too small for you to measure, because amplitude of 0.1 is quite a very small oscillation. But notice that in standing waves, because the waves interfere constructively, the amplitudes add up. And so if you use a very high amplitude to start with, then the amplitude will be out of range and it will be difficult to measure. Okay, but here you can see that standing wave that's generated using the first parameters in the first row of the table. So you can see this pattern is an arc throughout the length of the string. So if let me just draw that here so I can annotate. So if you draw the pattern that you saw, it's just it's one arc throughout the length of the string. So the green one is the string equilibrium position. So you can see that arc. You can of course draw the other side symmetrical to the equilibrium position. But if you can see here, this is the length of the string. So the green line, that's the length of the string, and the length of the string contains just half a wavelength, right? So if you draw your wave, if that's your wave, okay, one wavelength is, see, if you get that as the reference point, this will be one wavelength, right? That's one wavelength. The distance between two successive points will give you one wavelength. But here in the simulation, you get just half an arc. So that half an arc is actually from here to here. So that's what you've seen in the simulation. It's just half a wavelength. And that's why the whole length of the string is equal to half a wavelength, lambda over 2. Okay. Yeah, so the whole length of the string is equal to half a wavelength. It's just, yeah, it did not make one whole. Now, if you increase the frequency to 0.8 hertz, okay, what will happen if you increase the frequency to 0.8 hertz? Okay, right? Let's just wait for the amplitude to build up a little bit. Yeah, so you can see there the wave, the standing wave that is formed, that's generated. Okay? And you can see that the whole length of the string contains one whole wavelength, right? Because you're going from, yeah, after the rightmost part of the string, the wave will repeat itself, the pattern will repeat itself. And so within the length of the string, there is one wavelength of the wave contained in one length. So if I'll just draw that here, so the pattern you observe is like so. And if this is the length of the string, so if that's the length of the string, notice how you have length L. That's the length L of the string. Notice how you have one wavelength inside the length of the string. For the first one, you had half a wavelength. So if you write a relationship between the wavelength in terms of the length, okay, then you have move that here. Yeah. Okay. 2 times half a wavelength is equal to 1 wavelength. So within the length of the string L, you have 2 half wavelengths. Of course, this is lambda over 2, and the other half is lambda over 2. So you have 2 half wavelengths or 1 wavelength. You'll see why I'm writing that in terms of multiples of half a wavelength. We'll see that later on. But if we rearrange this equation to isolate lambda wavelength, you'll have 2 times the length over 2. And for the speed is equal to wavelength times the frequency. The wavelength is 2L over 2. Okay? And the frequency is F2. Okay, for F3, change the frequency, make it 1.2 hertz. So if you change the frequency and make it 1.2 hertz, okay, and I probably will not, I'll just do this. We're running out of time. Yeah, so notice how you have three antinodes, 1, 2, 3, and also 1, 2, 3, 4 nodes and 3 antinodes. So if I draw the pattern of the wave, so along the length of the string, you have 3 half wavelengths, right? So this is half a wavelength, that's half a wavelength, and this is half a wavelength. So you have 3 half wavelengths that's contained within the length of the string. We rearrange that, wavelength will be equal to 2 times L over 3. Rearrange this to isolate wavelength. And therefore, speed is equal to 2L over 3 times the frequency. Frequency is F3. If you do the same exercise for the 4th harmonic, F4, you will find that the pattern you'll see will be like this. Okay, so within the length of within the length of the string, you'll see that you have, that's half a wavelength, and half a wavelength. You'll see that you have 4 half wavelengths. Contained in the length of the string. If you rearrange that again to isolate wavelength, you'll have 2L divided by 4. And for the speed, you have wavelength 2L divided by 4 times the frequency is F4. So you can sort of, so the reason why I was writing the wavelengths in terms of half wavelengths is hopefully you can see a pattern emerging, right? For F1, which we call first harmonic or fundamental frequency, lambda is equal to 2L. For F2 equals second harmonic, which is just double. Yeah, if you compare this to second harmonic, is just double the frequency of the first harmonic. Okay. Notice how you have 2L instead, 2L over 2. And then for third harmonic, you have 2L over 3. Fourth harmonic is 2L over 4. Fifth harmonic, you can guess it's 2L over 5. Right. So you have a pattern there that your wavelength is equal to, I think there's, wavelength is equal to 2L over N. Okay, where N is equal to what we call the harmonic. N equals 1 for first harmonic. N equals 2 for second harmonic. And so on. And for the speed, you'll also see a pattern here. You have for the first harmonic 2L times F1, second harmonic 2L divided by 2, third harmonic 2L divided by 3, 2L divided by 4, and so on. So you have there a pattern for the speed 2L Fn divided by N. Okay. N gives you the harmonic. N equals 1 is first harmonic. N equals 2 second harmonic, and so on. So you can have a general equation for the wavelength and the speed of the harmonics. For the number of nodes, you'll also see a pattern. So node, that's the point, fixed point, okay, 0 amplitude point. So for the first harmonic, you notice there are 2 nodes and there's 1 antinode. Antinode is maximum amplitude. Second harmonic, you have 1, 2, 3 nodes and 1, 2 antinodes. Third harmonic, you have 1, 2, 3, 4 nodes, and you have 1, 2, 3 antinodes. So you'll see a pattern here. The number of antinodes is the harmonic, and the number of nodes is just harmonic plus 1. And if you divide the higher harmonic frequencies, so if you notice here, going from F1 to F2, you doubled it. But if you go F4 divided by F1, so F4 is 1.6. 1.6 divided by 0.4, that's equal to 4. F3 divided by F1, 1.2 hertz divided by 0.4, you get 3. F2 divided by F1, 0.8 divided by 0.4, you get 2. So as you can also see here, going from the first harmonic to the second harmonic, you doubled the frequency. Going from first harmonic to third harmonic, you tripled the frequency. Going from first harmonic to fourth harmonic, it's 4 times, oh, sorry, 4 times the fundamental. So you can also see a pattern emerging there in terms of the frequencies of the harmonics. Right? So the higher harmonics, meaning second, third, fourth harmonics, it's a whole number multiple of the fundamental or the first harmonic. So if you wanted to predict the frequency of the fifth harmonic, yeah, that's good. Thanks, Willow. So if you want to predict, yeah, frequency of the fifth harmonic, if you see the pattern here, fifth harmonic would just be 5 times the fundamental frequency. And I think I should write this better. Second harmonic is 2 times the fundamental, third harmonic 3 times the fundamental, fourth harmonic is 4 times the fundamental, fifth harmonic should therefore be 5 times the fundamental, which should be 5 times 0.4 will give you 2 hertz. Right, and you can set the driver to determine the fifth harmonic. Okay, how many antinodes should you have? You should have 5 for the fifth harmonic. F5 is equal to 2 hertz. You should have 5 antinodes and you should have 6 nodes. So if you draw that, you should have 1, 2, 3, 4, 5. Yeah, contained in the length of the string. Right. So that's the length of the string. You should have 1, 2, 3, 4, 5, 6 nodes, and you should have 1, 2, 3, 4, 5 antinodes. Yeah. 6 nodes. Okay. And to determine the speed of the wave, yeah, we have the general equation 2L Fn over n. Okay, for the fifth harmonic, the speed of the fifth harmonic wave will be 2 times the length times the fifth harmonic divided by 5. Fifth harmonic, of course, means n equals 5. So that will be 2 times the length, whatever length of your string, times the frequency of the fifth harmonic is 2 divided by 5. Right. Okay. Quite a long workshop. Developing the harmonics sort of takes a little bit of time. Yeah, and I think the simulation can help you visualize how the wavelength is related to the length. And from the visualization, we can get general relationships for the frequency of the higher harmonics, the wavelength, and the speed of the wave. Okay, any question on the workshop or the lecture or anything at all? Yeah, no questions. All right, cool. Okay, you're welcome, everyone, and thank you for coming to the lecture and the workshop. The recordings will be up on stream, and so will the annotated notes. If I don't see you this afternoon, have a good weekend, everyone, and I'll see you next week.